Okay, today we're going to be seeing if you can cook food with sound. So when you speak, it takes energy to do that. But where does that energy end up? It doesn't just disappear, because we know that energy can never be created or destroyed. It just moves to different locations and changes state. So does that mean it's possible to heat up a cup of water just by yelling at it? And could you actually cook food just from loud sound? So sound is the momentary compression and expansion of molecules. So as I speak, the air around me compresses and expands just a little bit, and those waves spread out as sound waves. But the question is, what happens to those sound waves as they spread out? Do they just keep bouncing back and forth and never go away? Well, you know from experience that that's not true. Eventually the sound in the room dies out. But why does the sound in the room go away? Well, the reason sound eventually goes away and doesn't just keep bouncing off and echoing around and around is because those ordered expansions and compressions of the air around you eventually become disordered. And disordered movement of molecules is just called heat. So you could almost say that sound is like ordered heat. And that means that you could heat things up with sound. But how much energy does sound actually have? Well, the energy of sound is related to its frequency. Lower frequencies have lower energy, and higher frequencies have higher energy. So lower frequency means that there's a bigger time gap between the peaks and valleys in the wave. And that's usually measured in hertz, or cycles per second. It can seem a little bit counterintuitive that higher frequency means more energy and lower frequency means less energy. Especially if you've ever heard loud bass playing, because you can actually feel that bass hitting your body. But if you want to see what I mean in terms of energy, just move your hand up and down. If you move slow, it's not that hard. But as you move faster and faster and faster and faster and faster and faster, it gets harder and harder. So it takes more energy to move faster, basically because you're doing more movements per amount of time, and so you had to put more energy per time. So high frequency means a lot of energy per time, low frequency means less energy per time. So in order to test if we can cook something with sound, I'm going to start out with some low frequencies and then just move up higher and higher and higher and see how high we have to get before we can actually cook something with sound. Okay, so I'm going to be using a tone generator here. I'm going to start off with the lowest frequency that humans can hear, around 20 hertz. Okay, so let's start off with a raw egg at room temperature. Okay, so I'm just going to put a little bit of egg on my cone here, the yolk part. And then I'm going to measure the temperature of it. So 82 degrees Fahrenheit to start off. Okay, so let's start off 20 hertz. Okay, so basically we just have a shaking egg right now. See if we're getting any energy from this. So the laser you see on it is me measuring the temperature. So about 80 degrees, so nothing really happened. Turn it up to 40. Let it sit there. So there's obviously some variability here. I'm getting around 78 degrees Fahrenheit. Turn it up to 80. Okay, we got 80 hertz. Nothing much, still around 80 degrees Fahrenheit. Okay, let's take it up a notch. 100 hertz. Still around 80 degrees Fahrenheit. Not doing much to the temperature, even though it's vibrating pretty extreme here. Let's turn it up to 200. Go to 320. So that's kind of a deafening sound right now. Still not increasing the temperature though. Let's go to 500. Still 82 degrees Fahrenheit. Yeah, so definitely not increasing yet. Let's up the power. Okay, we're at 1,000 hertz. Still no increase. My ears are aching. 2,000 hertz. Still no increase even at 2,000 hertz. Let's go to 4,000. Oh, that is horrible. Still no increase. 7,000 hertz. Still not even touching it. So this is moving up and down 11,000 times per second, which is quite amazing. Okay, so we're at the edge of human hearing now, so I can just hear this very faint buzz sound when I get close to it. You might be able to hear something. So, and finally, we're still just around 78, 80 degrees. No change at all in temperature. And it looks like for this app, we're at the edge of human hearing, but that doesn't mean we have to stop here. Let's go ultrasonic with my ultrasonic transducer. So these are used in sports medicine to treat sore muscles and other sore areas of the body. Okay, so let's put on our egg yolk. Okay, first let's measure the room temperature. About the same as before, 79.2 Fahrenheit. Okay, let's turn it to its highest setting. So look at the surface of the egg there. You can see that there's some slight atomization going on there. So you can actually see the temperature going up here. So the temperature is rising pretty significantly here. It's up to 82 degrees Fahrenheit. So it's at 84 degrees Fahrenheit now. So it's definitely heating up. Okay, we're at 90 degrees Fahrenheit. You can see the temperature rising pretty linearly because at this point it's just putting a constant amount of energy into the egg here. And really it's not just into the egg, but it's into the whole head of the transducer here. Okay, 100 degrees Fahrenheit. So you can see that even at 1,000,000 hertz, 1,000,000 cycles per second, it's still taking about 10 minutes to get to just 100 degrees Fahrenheit, just above body temperature. So with our other one too, we have 101.5 degrees Fahrenheit. But the problem here is that the temperature increase is so slow that as this heats up, the room temperature air just takes away the heat. So the rate of temperature increase is slowing down. But if you were to do this in a vacuum, then there wouldn't be any air to dissipate the heat. And so this could definitely continue to heat up so that it would cook the egg. The only question is would the internal components fry before the egg? Okay, so you definitely can cook egg with sound. In fact, when you use these ultrasonic transducers in sports medicine, you're not even supposed to turn it on unless it's touching the skin, because essentially there's no way to dissipate the heat or the energy coming from the sound unless you're touching it to the skin. My egg is kind of gelled up here into pretty much a solid on the ends here. Mostly this is due to evaporating the water, so we're just left with the dried egg yolk. But it definitely is hot or warm to the touch. Probably if I run it much longer than this, the internal components are just gonna burn out and break. So let's say you thought that was cool and you wanted to try to heat an egg up just by screaming or yelling at it. So the average human can yell at around 80 decibels, but although that sounds really loud, it's not actually that much energy. In fact, the energy is only about 0.001 watts when you scream. Compared to this ultrasonic transducer of 1,000,000 hertz, which puts out around 4 watts per centimeter squared. So if you were just screaming at a cup of water and putting out around 0.001 watts, even if all of that screaming energy was focused on that cup of water and you weren't losing any heat whatsoever, it would still take around 1 year and 7 months to even heat that cup up by 50 degrees Celsius. Hey everybody, thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did enjoy it and you're not subscribed yet, remember to hit the subscribe button and hit the bell to be notified when my latest video's out. And thanks for watching, and I'll see you next time.